This video will explore the concept of mechanical energy. We're going to look at three important forms of mechanical energy, meaning forms of energy that have to do with the motion or the movement of objects. And we're going to define just what energy means. Energy is a slippery topic because in general most people have some intuition about what energy means, but if you were to ask them what the definition of energy is, most people would not be able to tell you what that definition is. And in physics we have a very specific definition of what energy means, and energy is simply the ability to do work. It has units that are joules, which you may be familiar with. In the English system, those units would be calories, but in general we won't be using calories. We'll stick with the English version, or the metric version I should say. And obviously work must be pretty important since energy is defined as the ability to do work. And that means any form of energy that you can think of. For example, sound energy. Sound energy represents the ability to do work. Even though no work may be done, but still that energy represents the ability to do work. So since work is the definition of energy, then it must be a pretty important concept to understand. So let's take a look at the definition of work. Work is defined as the product of the force acting on a body and the displacement of that body. Okay, now there's a little bit of a tricky aspect to it though, and that is that only the part of the force that points in the direction of the displacement does any work. So if, for example, let's say that I was pushing or that I was pulling on an object, but I wasn't pulling exactly in the same direction as the displacement. So if, for example, my displacement was to the right, but let's say that I was moving a box along the floor, but I was doing it by pulling on it at an angle. I'm going to draw the force. So there's my force. And so not all of the force is actually pointed in the direction of the displacement. So I only get credit for the part of the force that points in the same direction as the displacement. So as a result, there is a part of the force. Part of the force points in the direction of the displacement, and part of the force points in this direction. So if you imagine an angle, and this angle that I'm identifying is the angle between the force and the displacement. So that's a little bit like torque. Torque was the angle between the force and the lever arm. Similar, this is the angle between the force and the displacement. This portion of the force right there would be the force times the cosine of this angle, and this guy would be the force times the sine of the angle. So if I take the force and I break it up into two parts, the part that points with the displacement and the part that points perpendicular to the displacement, this part right here doesn't do any work. There's no work done by this, but this portion I do get credit for. So the definition of work is the product of the force and the displacement, okay, but only the part of the force that goes in the direction of displacement is actually counted as doing work. So we add one more term, and that is the cosine of theta. Okay, the cosine of theta has no units. That is a number that it has no units. It's the ratio of two sides. So the units for this thing, if you just think about the units for force are newtons, and the units for displacement would be in meters. That should sound familiar because in the topic on, if you've discussed torque, torque also is in units of Newton meters, but the difference is it's not newtons applied over those meters. It's not Newton applied for a certain distance. It's newtons applied to a lever arm that has a certain length. So even though the units are the same, they are Newton meters, these units are a little bit different, and these units do produce what we will call joules. And the symbol for joules is capital J. So work is basically the energy represented by moving an object from one location to another. The force that's used to move the object from one location to another, that gets counted as part of the work. Others do not. So for example, as I move this pen across the table, I'm not technically doing any work on it because the force that I'm applying is in the upward direction, while meanwhile the displacement is horizontal. So the force points up, but the displacement points horizontally, so that force that my hand is applying is technically not doing any work. The only thing that could do work is friction. So the friction between my hand, and the pen, that actually points in the right direction. The frictional force points this way, the displacement's in this direction, so that I am doing work. So we'll talk a lot about work and when work is done and when work is not done. It can be a little bit tricky to identify when work is being done, but the important thing to remember is just that the force and the displacement need to point in the same direction. And when they do that, work is done, and when they don't do that, then there is no work that's done. So work is a very important form of mechanical energy. I'm going to put a box around the equation. Before we go any further, I want to take the units for joules and I just want to break them down into the most fundamental units, and those would be kilograms, meters, and seconds. So if I take this and I say that a joule is equal to a Newton meter, and just to remind you what a Newton is, Newtons are calculated by doing mass times acceleration. The mass would be in kilograms, the acceleration would be in meters per second squared, and then I would need to multiply those by meters again. So when I combine all of that together, a joule is equal to a kilogram meter squared, meters times meters is meters squared, and then divided by seconds squared. This is the third time that we've seen those units. So the first time we saw those units was the Newton. A Newton is a kilogram meter per second squared. Kilograms, meters, and seconds. The second time that we saw that was with momentum. Momentum was just kilogram meters per second. And here's the third time that we've seen it, the joule. A joule is a kilogram meter squared per second squared. And we'll see one more combination of these three units coming up a little bit later in this topic. So work is an important form of energy. It's probably the most important form of mechanical energy when you move an object. But there is another form that is related to work, which is called potential energy. So let me give you the definition of potential energy. So I showed you an example of the pen moving horizontally across the table. Okay, but if I were to move vertically, if I move the pen vertically, then I will be doing work because my hand will be applying a force in the upward direction, and the object will be displaced in that direction. But when I do that, there's another force that's also acting on the pen, and that is gravity. And since gravity acts downward on the object, when I push up on the pen, I force gravity to do this form of work that is negative, that is basically stored energy. So as I raise the pen up, I'm storing energy in the pen in the form of what is called potential energy. So the simple definition of potential energy is the work done on a body against gravity. So if I, for example, move an object upward, I give an object some displacement in the upward direction, but remember, gravity points downward. The weight of the object points downward. This energy that is done is negative, and the meaning of that energy being negative is that it has been stored. I've stored the energy in the pen. I can later recapture that energy if I just let the pen fall. So the definition of potential energy, and our symbol for potential energy will be EP. So the potential energy is EP, and it is force times displacement, but in this case the force that we're talking about is the weight, mg, and the displacement that we're talking about is the height. So how far I moved it, when I talk about a displacement in a vertical direction, we would typically refer to that as an h. So potential energy is equal to mgh. Now in most cases we won't really care how much potential energy we have. We'll mostly be concerned with how much did the potential energy change. So as we get later in the topic, we'll talk about transforming energy, and we won't be so concerned about the height, but more concerned about how much the height changed by. If it went from 2 meters down to 1 or from 2 down to 0, we'll be concerned with the change in height. Just to verify that this thing does give the same units as the previous one, the units for mass are kilograms. The units for g would be meters per second squared, and the units for H would be meters, which gives me kilogram meters squared per second squared. So that does give the same units as the mechanical energy we talked about with work. And in fact, potential energy is actually based on work, so I mean it should make sense that it does give the same units as work. And so now let's switch to the third and final form of mechanical energy that we're going to talk about today. And that form of energy is called kinetic energy. Okay, and kinetic energy is just simply, it is not about how you have moved it, it's actually the act of moving it. So while an object is moving, if it is in motion, it is said to have kinetic energy. So the definition of kinetic energy is simply the energy of the motion of the body instead of the energy associated with having moved it from one place to another. Potential energy and work are about moving it from one location to another, while kinetic energy is about the actual motion. While it's moving, it's said to have kinetic energy. Its definition is a little bit more complicated, has a slightly more complicated formula. So the kinetic energy is 1/2 mv squared. And just to show that this does produce the same units, the 1/2 of course has no units. The mass has units of kilograms. The velocity has units of meters per second, but I'm going to square it. And when I square it, I end up with meters squared per second squared. So that guy does have the same units as the work. So three important forms of mechanical energy: work, potential energy, and kinetic energy. W, EP, and EK. So before we go into more complicated problems, let's do a few simple problems. We'll do one problem for each just to show how a simple calculation problem would go. So let's look at this problem. And you might want to take a second to stop the video to copy the problem. I'll read the problem and then you might want to stop it so that you can focus on the solution instead of writing while you're listening. So the example says that Carla is pulling a 3.5 kilogram sled by a rope that makes a 40-degree angle with the horizontal. Determine the amount of work Carla will do if the force she applies is 23 newtons and the sled is moved by 12.5 meters. So first thing that we would do with this problem is we would write out all of the information that was given. So first of all, the mass of the sled is 3.5 kilograms. The angle theta is 40 degrees, and I'll draw a picture in a moment to show you what we're looking at. Determine the amount of work, so that's what we're looking for is work. I'll write that last. If the force that she applies is 23 newtons and the displacement is 12.5 meters. Okay, and again, what we're looking for is the W. So the formula for displacement, W is equal to F times D times the cosine of theta. Now, if the angle between the force and the displacement is 0 degrees, and you can test this yourself, take out a calculator and put in the cosine of 0 degrees, and you'll find that the cosine of 0 degrees is 1. So in the situation where the angle between the force and the displacement is 0, then it just turns out that the work is equal to F times D. So that's a little bit similar to like what might happen in the torque equation, except the torque equation is based on sine. So in that case, the angle 90 degrees causes the sine to be 1. In the case of the cosine, when the cosine of the angle is 0 degrees, then you end up with 1, and so the formula essentially just reverts to W is equal to F times D. If the force and the displacement point in opposite directions to each other, that would be 180 degrees. And the cosine of 180 degrees is -1. So in the case where the force and the displacement point opposite to each other, you get negative work. So work can be both positive or negative depending on whether the force goes with the displacement or whether the force goes against the displacement. So let me draw a picture over to the right of what's going on. So we have a simple sled and it's being pulled by a force that makes a 40-degree angle. There's a displacement of 12.5 meters. Okay, so the displacement is horizontal, so I don't get work done from all the force. I only get work done from the part of the force that is in the same direction as the displacement. So I'm going to need to use that angle. So W would just simply be 23 times the displacement, 12.5, times the cosine of 40. And we'll get a calculator. And so we're going to take 23 times 12.5 times the cosine of 40. I'll put the calculator in degrees. Try that again. 23 times 12.5 times the cosine of 40, and that says 220. So the work done by Carla pulling the sled is 220 joules. Now the 3.5 kilograms was not needed for this problem. The mass of the sled would affect the weight, which is vertical, but since there's no displacement in the vertical direction, then the weight is not doing any work. The normal force points up, but there's no displacement in the upward direction, so with no displacement, there's no work done. So the only work done is the horizontal work. So this was a horizontal problem. Let's switch gears and go to the potential energy. Potential energy is only going to be gained if we work in the vertical direction. So we'll do an example with the potential energy. It says, the second example says, calculate the amount of work required to lift a 1.45 kilogram book from the floor up to a shelf that's 1.7 meters above the floor. So not a lot of given information there. The mass was given 1.45 kilograms. And the shelf's height, 1.70 meters. Okay, so in this case, the work that's going to be done is going to be the potential energy. We're going to do work against gravity. Gravity's trying to pull down, and we're going to move the thing up. And so the work that we're going to do is simply going to be the potential energy, and that is mgh. So here's the force, here is the displacement, and so that is 1.45 times 10, and then multiplied by the height of the shelf. So making that calculation, 1.45 times 10 times 1.7, the height of the shelf, and that says 24.65. So we're going to say 24.7 joules. Again, the answer is in joules, just like the previous one. And that's it. So simple problem where we calculated the potential energy that was gained by lifting this book by 1.7 meters. We'll look at one last example. So we looked at work, we looked at potential energy, and the last thing to look at then is a problem involving kinetic energy. So we're going to determine which has more kinetic energy, a 750 kilogram car traveling at 20 meters per second, or a 1200 kilogram truck traveling at only 10 meters per second. So heavier truck, but traveling at a slower speed. So we'll compare the two. So I have one kinetic energy, and I have a second kinetic energy, and we'll compare the two. So in the case of the kinetic energy of the car, that would be 1/2 750 times 20 squared. And in the case of the truck, that would be 1/2 1200 times 10 squared. So making those calculations, we'll do the car first. That would be 0.5 times 750 times 20 squared. So that's a pretty large number. That's 1.5 times 10 to the 5, 150,000. And again, that's in joules. And then for the truck, which is heavier but not traveling quite as fast, that would be 0.5 times 1200 times 10 squared. And so that turns out to be only 60,000 joules. So EK is equal to 6.0 times 10 to the only the 4th joules. So in this case, the car. Even though the car is not as heavy, it made up for it with the velocity. And if you notice, the equation is 1/2 mv squared, so the velocity has a big impact on the amount of energy that you have. So for example, if you double your velocity, you'll get 4 times more kinetic energy. If you get 3 times more velocity, you'll get 9 times more energy. 4 times more velocity, 16 times more energy. So the effect of the velocity is much greater than the effect of the mass. The car is a little less massive, but it's a lot faster, and as a result, it has a lot more kinetic energy. Okay, so those are just 3 simple example problems in which we're trying to just make a calculation of the work, the potential, or the kinetic energy. So we're just going to summarize real quickly, and we're going to put all the equations side by side with each other. So the equation for work, W is equal to F times D times the cosine of theta. The potential energy is EP is equal to mgh, and the kinetic energy EK is equal to 1/2 mv squared. So we'll be using those 3 equations quite a bit in this chapter. We're going to start making combinations. So far we've been looking at simple problems where all we really needed to do was just use the formula and solve for W or EP or EK. Obviously, if I knew the kinetic energy, I could, for example, solve for V. If I knew the potential energy, I could figure out what the height that I had lifted the object. If I knew how much work was done on an object, I could figure out how much force must have been applied to that object. So these equations can be used to solve not only for W, EP, and EK, but also for any of the other variables that are in there. And in the next video, what we're going to do is we're going to start combining them together using an extremely important law called the law of conservation of energy. So this conservation of energy is going to let me transform this form of energy into this form, or this form into this one. Or I can transform both of these into this form. So we're going to combine these together, a lot like we did with forces, a lot like we did with torque, to produce new equations that will be solving specific problems where energy is being turned from one thing into another.